Hi guys. So this week we are moving on to an entirely different unit. So we are going to finally transition away from rational functions and we're going to start looking at exponential functions and log functions. So these next 2 weeks we're really going to focus on exponential functions. This is something you actually were introduced to back in Algebra 1. So today we're really not going to do a whole lot that you didn't see in Algebra 1, but it's a lot of good review. And then later this week we're going to actually transform these graphs by transforming the parent function like we've done all year, just with a new parent function. So the first thing we're going to do today with exponential functions, this is really the big thing for today, is understanding the difference between exponential growth and exponential decay. So these two graphs, even though your equation can be y equals b to the x or y equals a times b to the x, whichever format it's in, what the base is depends on the shape of your graph. And that's the thing that's really different about the exponential function. You have a lot of different bases that are possible. And what that value of that base is dependent on how your graph is going to look. So let's say, for example, you're doing that growth parent function and your base is greater than 1. Well, if that's the case, if the base is larger than 1, this is going to show growth. Because think about some easy points to plug in. If I plug in 0, anything to the 0 power is 1. If I plug in 1, no matter what base I have, anything to the first power is itself. If I were to plug in 2, then the base would be squared. If I plugged in 3, it would be cubed. But if I plugged in -1, this would be 1 over b. And if I plug in -2, it would be 1 over b squared. So that's going to keep getting smaller and smaller and smaller. So this graph is going to go through 0, 1, and then it's going to get much, much larger, much quicker to the right, and then smaller and smaller and smaller to the left. But one thing that you'll notice, though, even though it's getting smaller and smaller and smaller, no matter what that base is, it's never going to cross the x-axis. Because there's no way to take some positive number that's greater than 1, whether that's 2, 2.5, 5, 10, and raise it to any exponent, any sort of an exponent, that's going to give me a number that's negative. So these exponential functions are going to have a horizontal asymptote. Now, like I said, depending on what that decay or what that base is, your graph could also show decay. All right, so let's say that base instead, let's say that base was 1/2. So 1/2 falls between 0 and 1. Well, again, if I plug in 0, it doesn't matter what the base is. 0, 1 is going to be a point on this graph. But if I used 1/2, 1/2 to the first is 1/2, which is going to be lower. 1/2 squared would be 1/4. 1/2 to the third would be 1/8. So those values are going to keep getting smaller and smaller and smaller. Now again, it's not going to cross 0. But if I raise that to a negative exponent, 1/2 to the -1 would flip that and become 2. 1/2 to the -2 would flip that and become 4. 1/2 to the -3 would flip that and become 8. So the more negative my x's get, the larger my value gets, which is why if that base is between 0 and 1, that graph is going to show decay. Now again, these graphs, really when we come to graph when we start talking about the parent function next week, it's really going to have four important features, 3 points and an asymptote. So it's going to have that horizontal asymptote at y equals 0. The parent function is going to go through 0, 1, 1 comma the base, and -1, 1 over the base. If you want another point, you also can use 2 comma the base squared. So those are all points that are going to be on this parent function. Now, a few features that are on here, when we have an equation in this form, and we're going to look at a different form when we get to our parent function, but this is kind of your basic growth decay form. The reason for that, first of all, notice a does not have an exponent. This is a times b to the x. So let's say this was 2 times 3 to the x. That is not the same thing as 6 to the x. Okay, we cannot multiply those numbers together. That a value is your initial amount. So when we get to application, that's going to come up a lot to where that first number is your initial amount, your starting amount, which in this case is our y-intercept. B is the growth factor or the decay factor. And again, it depends on the value of that base, if it's larger than 1 or between 0 and 1. Now you'll notice it's between 0 and 1. It's not just less than 1. So a couple reasons for that. That base can't be negative. Because if that base is negative, let's say this was a -3. Well, let's say I raise -3 to the x power. Well, there's a couple problems with this. First of all, let's say that if x is 1, then I would get -3. Well, when x is 2, I'll get positive 9. When x is 3, I'll get negative 27. When x is 4, I'll get positive 81. So this graph is just going to go up and down like crazy. But even worse than that, it's going to have a bunch of holes. Because if I take negative 3 to the 1/2 power, that would be the square root of negative 3, which is imaginary, which I can't do. So we're going to run into a whole lot of problems if that base is negative. So you'll see negatives potentially in these, especially when we get to transformations, but the base itself is not negative. Okay, that negative is being multiplied by the base. All right, so let's go ahead and look at a couple examples here. Really, the most important thing for us to be able to determine is whether or not this is showing growth or decay. And all we need to do to determine that is look at the base. So looking at this first one, the base is 3. 3 is greater than 1. This is showing growth. On the next one, the base is 3/4. That's less than 1. So this is showing decay. So that means both of these graphs are going to have that horizontal asymptote at y equals 0. However, the first function is going to go in this direction because it's showing growth, whereas the second function is going to go in this direction because it's showing decay. All right, specific points. If you want, again, it says to label 3 points, 0, 1, 1 comma the base, and negative 1, 1 over the base. Same thing for the next one, 0, 1, 1 comma the base, and negative 1, 1 over the base. Now remember, 1 divided by means reciprocal, so that's just 4/3. All right, looking at the next one, even though there's a 2 here, that does not change the fact that this graph is decay because the base is smaller than 1. That's what we really look at to determine decay. So the shape of this graph is going to be getting smaller as it goes towards the right. So again, 3 points, 0, 1, 1, and this one's a little different because of that 2. So if I plugged in 1, this would be 3/4 to the first, which is 3/4. 3/4 times 2 would be 6/4, which reduces to 3/2. If I plugged in negative 1, then I would do the reciprocal, which is 4/3. 4/3 times 2 is 8/3. So those are 3 points on that graph. All right, and the last one, 5/4. That shows growth because that base is larger than 1. So it's going to have this direction. And then 3 points on this graph, 0, 1, 1 5/4, and negative 1 4/5. All right, so now we're going to look at a new base, and this is going to be a really important number for you going forward. So this base is the letter E. So the letter E is what's called Euler's number. So that name right there, again, it's pronounced Euler, not pronounced Euler. Okay, what the letter E is it's a constant. It's kind of like pi. So you know how pi stands for 3.14159, and it keeps on going and going and going? E is very similar. Okay, it's a constant that stands for a specific value. So there's a couple different ways that you can estimate it. One of them, it's basically this expression as x approaches infinity. So what that means is as x gets bigger and bigger and bigger and bigger, this value is going to get closer and closer and closer to the actual value of E. So what we can do, we can start by plugging in 10. And you'll need a calculator for this, and I think I have one with me. So I'm going to start by plugging in 10 to my calculator. So 1 plus 1 over 10 to the 10th power is what I'm going to plug in. And if I plug that into a calculator, I'm going to go a couple decimals past so you guys can see. This is 2.5937. All right, now I'm going to use the same expression, but I'm going to plug in 100. So then that's going to give me 2.7048. Same thing, but plug in 1,000. 2.7169. Same thing, but plug in 10,000. 2.71815. Keep going, 2.71827. And then finally, I'll get 2.71828. So again, the higher number we plug in, the closer and closer and closer we're getting to the value of E. So if you'll notice, every single time it led with 2. So for sure it's going to lead with 2. Then as that number got bigger, the second digit was always 7, or the first place after the decimal was 7. Then it was always a 1. Then it was always an 8. And then both of these were 2. So as it keeps going, you'll get closer and closer and closer to E. So the way we're going to estimate it, we're going to say it's approximately 2.718. All right. Another way you can estimate E is using this factorial formula. So if you haven't seen factorials before, that's okay. I'm going to briefly talk about what they are. Basically, a factorial means you take that number and you multiply it by every integer smaller than that number. So 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1. 4 factorial would be 4 times 3 times 2 times 1, so that would be 24. 5 factorial would be 5 times 4 times 3 times 2 times 1, which would be 20 times 6, which is 120. So as those values keep getting larger and you keep adding them together, you're going to get closer and closer and closer to that 2.718 value. And again, the 2.718 keeps on going and going and going forever. Interesting thing about these factorials, this may be not as interesting for you guys, but last week actually, one of our days was 8 factorial day. So 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Well, if you go ahead and multiply that whole thing out, you end up with 40,320, or 4,320. So April 3rd of this year was actually 8 factorial day. And then the last thing about E, something that's really unique about it, it's going to be really important when you get to calculus. The function y equals e to the x. So look something like this. It's obviously showing growth. Something pretty unique about that is if you take some point on that graph, like let's say I take this point right here. If I were to find the slope of the tangent line at that point, so I'm going to draw a tangent line, and I'm going to find the slope of that. Well, the y-coordinate of that point is going to be the same thing as the slope. So at this point, the y-coordinate's 1, because it goes through 0, 1. Well, the slope of that tangent line at that point is also 1. Now that's true if you take any point in this graph. So like if I go to when x equals 1, then y equals e, okay? Well, at that point, the y value is 2.718. The slope of the tangent line there is 2.718. And that's going to be true for any point that you pick on that graph. And that's just kind of a cool application and the reason that E is going to be really important in calculus. All right, so what we're going to do now, really guys, the next section is just reviewing your exponent properties. Because remember, E is a base. Now it's not a variable, this actually stands for a number, but our exponent properties are still going to apply. So e to the third times e to the 7th is e to the 10th, because I can add those together. Remember, e to the 10th does have a value to it, and you could plug that into your calculator if you needed to. All right, again here, using exponent properties, 25 divided by 5 is 5. I can subtract those exponents, so this is just 5e. On C, both of these components are going to get raised to the 5th power. And then if you remember, negative exponents move to the bottom, so 2 to the 5th is 32 over e to the 15x. So really that's just a review of your exponent properties. All right, so now again, we're going to go back to talking about graphs for a second. So until this point, we talked about growth and decay just by looking at the base. If the base was greater than 1, then it showed growth. If the base was less than 1, it showed decay. Well, there's another way to show growth and decay based on whatever your base is, and that is based on the exponent. So if you look at this, y equals e to the x. Well, based on everything we've already talked about, should have a horizontal asymptote, should show growth, should go through the points 0, 1, 1, 2.718, and negative 1, 1 divided by that. So that would be our e to the x function. Well, a way I can still have a base of e and show decay is with a negative exponent. And we're going to talk about this a lot more next class, but think about the transformation that's happening there. Negative near the x is a reflection over the y-axis. So if I reflect this graph over the y-axis, I am now showing decay. Again, if I plug in 0, I still get 1. If I plug in 1, this would now be e to the negative 1, which is 1 over e. If I plug in negative 1, well, negative 1 is just 1. So e to the first is just e, or 2.7. So that's why that shape is changing. So again, all we're going to do here in this next section is just determine, is this growth or decay? So we first look at the base. The base is e. Then we look at the exponent. The exponent is negative. That means this graph is showing decay. All right, on the next one, look at the base. 0.3 is not the base. 0.3 is just multiplied. E is the base. The exponent is positive. So this is showing growth. Then looking at the next one. E is the base. The exponent is negative. So this is going to show us decay. So two different ways we can see decay, okay? If the base is between 0 and 1, or if the exponent is negative. Both those things will show decay. All right, now the last thing we're going to do is we're going to take these exponential functions and rewrite them in a different form. And the form we're going to use is going to be one that's really helpful for us, especially next week when we look at applications and showing us growth and decay rates. So what we're going to do is we're going to rewrite this function. So 2 to the 2x, I want to rewrite it into the form a times b to the x. Well, how I can do that is using exponent properties. If 2 times x are 2 and x are multiplied together, that means you have a power to a power. So 2 to the second to the x power is the same thing. Well, 2 to the second power is just 4. So 2 to the 2x is the same thing as just y equals 4 to the x. That's another way to write that out. So we're going to use that concept to rewrite some of these problems. So right here, I'm going to go ahead and rewrite this, okay? I want it to eventually be in this form. The reason I'm going to use this form, okay, this form is going to show us growth, and this form is going to show decay. Because again, if it's 1 plus r, it's going to be greater than 1. If it's 1 minus r, it's going to be less than 1. Less than 1 is decay, more than 1 is growth. Now this is going to be a calculator section, so go ahead and get a calculator out. If you don't have one, you can use the VMware app on your iPad, or you can use another type calculator that you can find on the internet. But again, that VMware, there's a link on Schoology that shows you guys how to get into that. All right, so what I'm going to do is I'm going to rewrite this using our properties. So using our properties, we just said if this is x divided by 3, that's the same thing as 2 to the 1/3 to the x power. Because again, those power to powers you would multiply. Well, 2 to the 1/3 is something I can actually evaluate with a calculator. So at this point on a calculator, go ahead and type in 2 to the 1/3, and you should get 1.26. Again, I just got that from plugging that into a calculator. Well, now I need to determine, is this growth or decay? The base is greater than 1, so this is showing growth. Since it's showing growth, I want to rewrite it in this form. Well, 1.26 is the same thing as 1 plus 0.26. So at this point, the reason we want to write it in this form, 0.26 is actually your growth or decay rate. So 0.26 as a percentage, move the decimal 2 places, and we can see that that is 26%. So not only is this showing growth, we can specifically tell that this is showing 26% growth. All right, on B, same idea. We're going to rewrite this as 0.5 to the 1/12. Then at that point, I can go ahead and evaluate 0.5 to the 1/12 on a calculator, which would give me 0.944. At this point, I can determine whether or not this is growth or decay. This is going to be decay because the base is less than 1. So I'm going to rewrite this as 1 minus 0.056, which allows me to see the decay rate. Okay, 0.056 as a percent is 5.6%. So this is decaying with a percentage of, this is a 5.6% decay. All right, we're going to do the same thing this next one, but again, this one's just going to be in terms of E, but we're going to use the same method. Okay, so I'm going to start by rewriting this. This is going to be e to the negative 0.5 to the x power. And at this point, we're going to go ahead and plug this in on a calculator. Now let me pull up the Casio in case you guys don't know where the e is. All right, so e, if you do shift ln then you'll see e to the x is right there above ln. I know it looks like in, but that's actually in a lowercase ln. We'll get to that in a few weeks here. But that's where you'll find e to the x. Now, it's going to force you to use an exponent later on, or at some point, if you want to just type in regular old e, if you go ahead and do shift e to the x, you can just make it e to the first. But in this case, on this particular example, we're doing e to the negative 0.5. So now I can rewrite that as 0.607. Oops, sorry. That's not negative 0.607, it's just 0.607. So now this is obviously showing decay because the base is less than 1. We also know it's decay because the original problem had that negative exponent. But now I can rewrite that. This is going to be 1 minus 0.393, which means not only is it decay, specifically it is a 39.3% decay. All right, and then looking at the last one. Again, 0.5, okay, that is that leading kind of coefficient there. That 0.5 is that y-intercept. It has nothing to do with what's being raised to that power. It's not part of the base. The only base is e. So this is e to the 0.8 to the x. E to the 0.8 we can evaluate with a calculator. So this is 2.226 to the x. So this again is showing growth. So I'm going to rewrite this as 1 plus 1.226, which means that this is showing growth, specifically that rate. Remember, that's just the rate, that's not the percentage. Move your decimal 2 places to get your percent. This is 122.6% growth.